Hello everybody. Today we're going to learn how to write neutral formulas for ionic compounds. I will have a little shortcut method for you that makes sure we can do this quickly. We do need to understand the concept behind what we're doing is that we're trying to make the charges cancel out, and so we're trying to figure out how many cations and how many anions do we need. But we need a quick, fast way to do this so that we can do longer and more involved problems for the rest of the year. So first, let's look at neutral compounds. So we need them to be electrically neutral, meaning that we need to not have a charge at the end. These compounds will be made of charged particles, but we need the plus and minuses to balance out. And the thing is, it's not always going to be a one-to-one ratio. You don't always have one cation and one anion. In this example, if we have sodium and bromine, a +1 and a -1 cancels out and it is neutral. So that's nice. It's a one-to-one ratio. However, if you have calcium and fluorine, this is not neutral, right? A +2 and a -1 is not going to be neutral. What we end up needing is two fluorines. So calcium fluoride is CaF2, and that way the fluorines will balance out this calcium. Sometimes it's a little trickier. If we have aluminum, it's a +3. Oxygen is a -2. So at least back when I was in school, in math class, they would often refer to least common multiple. I don't know if that's still the phrase that they use. You know, the idea was that you're trying to find the smallest combination of the numbers to get what you want. And so for something like this, you know, if we put in an extra oxygen, well, now we have too much negative charge. So we add an extra aluminum. Well, now we still have too much positive charge. Finally, we add a third oxygen and everything balances. So the smallest common, the smallest combo that we can have that's neutral would be 2 aluminums for a +6 and 3 oxygens for a -2. This will all balance out and be neutral. Now, I don't know about you, but I really don't want to have to sit there drawing little circles on my paper, right? So we will have a shortcut so we don't have to do that. One thing you got to be careful of is that we're always using the smallest combo. This is good, 1 and 1. If we have 2 sodiums and 2 bromines, yes, this would be neutral, but this is not the smallest ratio we could have. 2 to 2 is going to simplify down to 1 to 1 ratio. So that's something we want to be on the lookout for, is that you're not making your compounds bigger than they need to be. We are going to use something called the crossing over method. So eventually we'll be able to do this in our head. If I ask you to show work in the beginning when we're learning how to do it, or on a quiz question if I ask you to show your work, you're going to do it a certain way. What you're going to do is you're going to write the cation first on the left, and then you write the anion. You're going to write the charges that go with each. Then you're going to do this thing called crossing over, which I'll show you in a minute. You're going to check that you have the lowest ratio possible. If you have a 2 to 2, shrink it down to 1 to 1. If you have a 2, 4, shrink it to a 1 and a 2. You're going to reduce things down. You do not need to put the 1s as your subscript. You don't have to tell me, just like in math, you don't say 1x. You're not going to tell me if there's 1 atom. And then you're going to be very, very careful with your polyatomic ions. Polyatomic ions are traveling around as a little package. You don't break them apart. And so your charge is going to need to be applied to the entire packaged unit. And so we're going to use parentheses to help us remember that those packages have to be treated as individual objects. So let's look at barium fluoride. First thing I'm going to do is I'm going to write the elements with their charges. I'm going to put the cation first and then I put the anion. Now, if I take this superscript and I cross it over down here, that's going to tell me how many fluorines to use. The minus up here is the -1. Now, I'm counting objects, so I don't care if it's a minus or plus, so I'm just going to use a 1. I'm going to take the 1 down here, and that's going to tell me how many bariums I need. So, barium fluoride is 1 barium and 2 fluorines. I cross over the subscripts to quickly and rapidly find the combo that I need to get neutral. Let's look at barium nitrate. I have my cation, I have my anion. And if you notice, I put parentheses around my polyatomic ion. The -1 charge is being applied to this entire packaged unit. Anything inside the parentheses, you cannot change. Never, ever, ever get rid of this 3. You cannot change that. Nitrate is 3 oxygens bonded to a nitrogen. That cannot change, okay? If you change that, it's not nitrate anymore. So when we cross over, you're going to take this 2 and you're going to put it outside the parentheses. You have 2 of these packages, okay? The 1 comes down here. I kind of make it look all pretty, get rid of all the junk, and I get barium nitrate is 1 barium atom, and it's 2 nitrate packages, okay? I have 2 nitrogens, I have 6 oxygens all together, but because they come bonded in this little packaged unit, I'm not distributing this out. I'm not going to write BAN2O6. I'm not doing that. I have to keep this as a package or nobody will know how to draw this later on. Leaving polyatomic ions as packages is very important to the structure, and that's what we'll learn a little bit later in the chapter. You can have 2 polyatomic ions. You could have ammonium sulfate, for example. Ammonium is +1. Sulfate is -2. The 1 crosses over, the 2 crosses over. In order for this to be neutral, I need 2 ammoniums and I need 1 sulfate package. Do not distribute this out. Leave it in parentheses. Leave it as a little packaged unit. You have 2 of these packages. When you have Roman numerals, remember the Roman numeral is telling you the charge on your transition metal. So if you have iron 3 chloride, that's telling you that iron has a +3. You know it's plus because it's a metal. It's going to be a cation. Chlorine is a -1. I know that from my periodic table. It's in that column where fluorine is. That's a -1 column. The 3 comes down, the 1 comes down. My formula is iron. Chloride is FeCl3. Okay. Why don't you try this next one? Write the cation, find the charge from the periodic table. Write the anion, find the charge from the periodic table. Cross them over. Rewrite it so it's nice and pretty and get rid of all the junk. In order for this to be neutral, you're going to see that you need 2 aluminums and you need 3 sulfides. People are constantly asking me, how did you know it was +3? How did you know it was -2? That's because I know the pattern on the periodic table. You got to memorize it. You have to know when you look at that table and you see aluminum in column 3 that that's a +3. When you see sulfur in that oxygen column, you got to know that's a -2. All right, try this one. We have magnesium carbonate. If you don't know your polyatomic ions, you're not going to know what carbonate is. Carbonate is not on that periodic table. It is polyatomic. Magnesium is in column 2, so it's a +2. I have memorized that carbonate is CO3 2-. I cross over, and everybody writes this, and then nobody gets any points, okay? We forgot to do something. This is not the smallest ratio, is it? I don't need 2 magnesiums and 2 carbonates. Reduce those down. It's just MgCO3. We just need one of each. So make sure that you're writing the simplified version, the one that's reduced, okay? All right, try this one. This one is tricky because this is a transition metal, but it's one of 3 that we have to memorize the charge of. Zinc is not variable. You need to memorize what zinc is. And hydroxide is polyatomic, and you have to memorize that as well. You need to be able to write the formula for something in 15 seconds. And if you have to flip to a notebook and look to see what the formula is and look to see what the charge is, you're going to run out of time. You have to instantaneously know that zinc is 2+. You need to instantaneously know that hydroxide is OH-. You have to know them instantly. If I ask you how to spell the word the, you better not go look it up in a dictionary, right? Remember our analogy of trying to write your 10-page English essay? If you have to go look up how to spell the word at, you're never going to finish anything. This is the equivalent. You must know what zinc is. You must know what hydroxide is. You have to be able to cross over as fast as you can in your head. And you have to be able to tell me that zinc hydroxide is 1 zinc atom and 2 hydroxide packages. Right? We have to be able to do that quickly. Okay? All right, try this one. Last one. Aluminum phosphate. One is going to require the periodic table location trick. One is going to require that you've memorized your ions. Aluminum 3+ because it's in that 3rd column. Phosphate is PO4 3-. Do not mix it up with phosphite or phosphide. Okay? Things ending in ATE, ITE, IDE, right? They all sound really similar and they are all very different. I cross over. I get my formula. I'm being careful to write the smallest version possible. I'm going to reduce my subscripts. And I'm going to find out I just need one of each. Now, if you just have one polyatomic ion, you don't technically need to have parentheses. I like to write the parentheses because I like to remember that phosphate is a package. And so I think it's helpful to put them, but it's kind of like in math class, if you have 1x, you don't have to put the 1. If you only have one polyatomic ion, you don't have to put the parentheses. Okay? So please, please, please practice writing your formulas. Writing neutral compounds is one of the most important skills of the year. Being able to name things, write formulas, dimensional analysis, right? Those are foundational skills for the whole year, right? Memorizing these ions, that's our alphabet, right? You gotta know your alphabet. Putting them together is like making a word. When we start putting these together, it's like making a sentence. When we write a reaction, we're writing a sentence. We put those reactions all together, we find out how many grams we have, we can predict how much we're going to make, we can do a bunch of math. That's the equivalent of our essay. You can't write the essay if you have to look everything up in the dictionary, okay? So please practice. It's going to help you long term. So one last thing that I want to go over about writing neutral compounds is that sometimes you're asked to go backwards, where you're given the formula for a compound that has a transition metal in it, and you need to write the name. And so you're going to have to kind of work backwards and kind of act like it's a little number puzzle to be able to figure out what charge was on that transition metal so that you know which set of Roman numerals to put into the name. So let's do a couple examples. We know we have an iron ion, but we don't know what the charge is. We also know that we have bromine here. Remember, we rename it to be bromide, and based on its location in the periodic table, of it being in the halogens, column 7A, we know that it makes a -1 charge. So we can now look at our subscripts and see, okay, I have 1 iron and I have 2 bromides. Well, if I use a little bit of problem solving here and I work backwards like a little puzzle, I can figure out, well, the 1 had to come from the bromide. That means the charge on that iron had to have been +2. I have 2 -1 objects, and they need to be canceled out. But I only have 1 of these objects. So this had to have been +2. That's going to make it iron 2 bromide. I have a +2, and I have a -1, and I have 2 of them. That's how I end up with iron 2 bromide. Some people are better at little number puzzles than others. Some people might find this super easy. Some of you may just need a little more practice. And that's totally fine. We have lots of practice we can do. Let's do another one. We know we have some kind of copper cation here. We know we have nitride. Based on its location in the periodic table in column 5A, we know that it makes a -3 charge. I look at my subscripts and I can see that I have 3 coppers. I only have 1 nitride. So over here, I have a total of a -3 and 1 object. Over here I have 3 objects, so I have to figure out what their charge needed to be. Well, this clearly came from up there, which means this came from over there, which means this is copper 1. So copper 1 and a nitride, we name that copper 1 nitride. If you ever want to double check that you got it right, just try crossing over again with the new ion that you have, right? And see if it works. The last one's going to be a little bit tricky. I think the last one is about as hard as this gets. This is gold. We don't know which ion. And we have oxygen that got turned into an ion based on its periodic table location of column 6A. We know that this is oxide, -2. We look at our subscripts. We only have 1 gold. That should seem strange to you. We only have 1 oxygen. This should look strange because if we were to cross over, you wouldn't expect a 1 here, would you? You would expect there to be something else over here. What's going on, the reason these don't match is because it was reduced. Remember, we always reduce to the lowest numbers possible, and so that's what's throwing us off here. We should know this is not a 1, and this is not a 1. This had to have been a 2. And then in order for this to cancel out, we would have needed this to have been a 2 as well. Once they get reduced, they look like 1s. A +2 and a -2 cancel out, right? And so this one is pretty tricky. This is gold 2 oxide. If we put the gold 2, we can see a +2 and a -2 cancels. That's why we only need a 1 and a 1. This is about as tricky as it gets. The nice thing is, most of the time, we're not writing formulas and names with transition metals. And when we are, we're usually not doing really, really weird ones like this, where you're trying to go backwards with something that was reduced. Okay? If you can do one of these, you can probably do any of them. I think this is about as hard as it gets. All right, everybody, that's it. I hope this was helpful. Bye. All right, that's it for this. I hope that was helpful. Bye, everybody.